Alright, in this section we're going to extend the 2D dimensional Cartesian space into a 3D dimensional Cartesian space by adding an additional axis called the z-axis. Alright, so let's look at this setup. You notice that this is the x-axis and this is the y-axis. They are perpendicular to each other, and on them you can actually find the base vectors, the I and the j. Right. So as an addition, we have the z-axis, which is perpendicular to both the x-axis and the y-axis. Alright, and similarly to what we have on the x-axis, the base vector I, and then the base vector j along the y-axis, we could also have another base vector we call k, which actually falls on the z-axis. Alright, as discussed before, the column vector for I is written as 1 0 0. Notice it's a 1 unit because this length is 1 unit, and similarly for j as well, this length is 1 unit, so you have a 0 1 0. This is the y component, 1 unit, and thus for the base vector k, we would also have 0 0 1, and this is 1 unit because we would expect this, the base vector, to have the magnitude of 1 unit as well. Alright, similarly to the 2D dimensional Cartesian space, okay, for the 3D version, any point P with coordinates x, y, z, it can be written as xi plus yj plus zk, or in the more popular form of writing, alright, it will be x, y, z, where x is the x component, y is the y component, and z is the z component. Okay. The magnitude of the vector OP, if it is in 3D, alright, is basically the magnitude of xi plus yj plus zk, and the magnitude is given by this formula. Alright, it's just an extension of the 2D. Okay, the unit vector is given as the vector divided by the magnitude, because this is the magnitude, so we take the vector divided by the magnitude, or in column vector form is essentially the column vector x, y, z divided by the magnitude. Alright, one thing that you need to take note of is that if I were to give you a vector OQ in terms of A, B and C, this does not mean that OQ is actually equals to 1, 2, 4. Alright, because I did not say that A is actually the base vector I, B is the base vector j, and C is the base vector k. So if it's not stated, you cannot imply that OQ is 1, 2, 4. That means OQ is just the vector A plus the vector 2B plus the vector 4C. Alright, unless of course A itself is the base vector I, B is the base vector j, and C is the base vector k. Alright, one extensively used result is this. When you have two column vectors which are equal as presented here, it can only mean that the x component are equal, the y components are equal, and the z components are equal. Some quick example, I will leave it to you for you to figure out the solution because it's all printed here, but just to take note, the recap of the unit vector, the symbol is u hat, and what it means is this unit vector is actually obtained by taking the vector itself divided by the magnitude. In this example, I will still let you to go through the example yourself. It's quite actually easy to follow. The only thing that I would like to take note of is that the question actually say find a vector of magnitude 3 units parallel to this vector, which can be written as this column vector, and the answer we get is actually this form. So the other question is, can the answer for this example be a vector which is similar to this but in the opposite direction? For example, this. So if this is the answer, are we also answering this question? So something for you to figure out. Alright, let's look at another example which involves column vectors. So the vector A is given as 2i minus 6j plus 3k. It can be written as this column vector, and B, it can be written as this column vector. Part A, you're supposed to find the magnitude of vector A minus vector B. Part B, you're supposed to find the magnitude of 2 times the vector A plus 3 times the vector B. Right? So these two examples are actually quite simple. I will just reveal the solution and let you take note of the working yourself. In example 9, you are given the position vector of points A, B and C as the column vector A, the column vector B and the column vector C respectively. In this question, please take note that for the vector C, there is an unknown x component. Alright, so what are the things that we need to do? We're supposed to find a unit vector parallel to AB. You're supposed to find the value of P such that A, B and C are collinear, and if given that P is -2, you're supposed to find the position vector of the point D such that ABCD is a parallelogram. Alright, so how do we find the unit vector parallel to AB? First thing, of course, we need to find out what is the vector AB itself. So vector AB, we already know that it's actually OB minus OA. Alright, by putting in the column vectors, we will get this. And this happens when you take the vector B minus the vector A. So 1 minus 4, you get -3. 3 minus -9, you get 12. 5 minus 1, you get 4. Alright. So to get the required unit vector, of course, we need to know the formula for getting the unit vector is actually we take the vector AB, we divide by the magnitude. Alright, this will give us the required unit vector. Alright, so therefore that's why we want to find the magnitude of AB. So using this formula, right, we should be able to get the required unit vector. Alright, next we are asked to find the value of P when A, B and C are collinear. Alright, so when A, B and C collinear, so that means our objective is to show this kind of relationship. AB equals to a scalar multiple K times BC. Alright, or if we wish, we can also use this relationship instead. So just make sure that we have a point in common on both sides of the equation. So in this case, the point common is B and B. Alright, so first we need to go and find what is BC. So BC is C minus B. So according to the column vectors given to us, we get this. Alright, because there is an unknown P. Right. So since A, B and C are said to be collinear, it must satisfy this relationship. Therefore, using the AB that we have found earlier on, alright, so this is AB equals to K times of BC. So we get this. So by the property of column vectors, as mentioned before, if these two vectors are equal, that means the X component are equal, the Y components are equal, and the Z components are equal. So we will actually get 3 equations. Alright, so from the 3 equations, we will be able to find out what is the value of K and what is the value of P itself, which is our intended outcome of this question. The last part of this question, we are given instead that P has a value of -2, and then we're supposed to find the vector D, alright, such that ABCD is a parallelogram. So being a parallelogram, we can choose any two of the sides. So in this answer, we're going to look at AD being parallel to BC. Right? So that means they are exactly equal vectors. So we need to equate them. Right? And previously, we found that AD on this parallelogram is actually OD minus OA. Alright, OD minus OA. So that means OD minus A. And BC we have already found. Alright, so from here we can actually make OD the subject, and BC, like I have mentioned, we have already found. Therefore, we can just shift the A over to this side. Then we will be able to get the position vector of the point D as intended in the question. Now, the ratio theorem is a very important and useful theorem for vectors. Alright, so what does it say? Alright, so if a point P divides the line segment AB, so this is a point B. Alright, so it divides the line segment AB, in the ratio of lambda is to mu. Alright, so if we know that the position vector of B is actually B itself, the position vector of A is A itself, we can actually find the position vector of this point P. Alright, and the position vector of this point P with reference to the origin here is given by this formula. So how do we read this formula? So basically the vector OP is equals to lambda times OB plus mu times OA, and then you divide by the total parts in terms of the ratio, which is lambda plus mu. Thus we have this formula, OP is equals to mu times the vector A plus lambda times the vector B divided by lambda plus mu. Alright, so the proof for this formula is given here. It is easy to follow, so I will leave it for you to actually look through. Alright, one specific case of this ratio theorem is what we call the midpoint theorem. Basically the midpoint theorem, it means that the lambda and the mu are exactly the same. Right, so one part and one part, so therefore the total part will be 2, and 1 times OA plus 1 times OB, right, because they are equal parts, so the parts here will be 1:1. Alright, in some examples, when we want to implement a ratio theorem, we purposely make the ratio into the form where this portion, alright, is maybe we call it beta, and this portion we call it 1 minus beta. The reason for this is we take the whole length as one part, so this one is just beta of the one part, and the remaining portion is of course 1 minus beta. Now how is this setup useful? This setup is useful, okay, for example, if I were to write down the position vector of P using this new setup, alright, you will realize that OP using the ratio theorem, alright, you have a beta times A plus 1 minus beta times B, and then at the bottom you will actually have beta plus 1 minus beta, and you soon realize that in the denominator now the whole thing actually becomes 1, such that the position vector of our OP will just become beta A plus 1 minus beta B. And this is useful. Why? Because when we are working with unknowns, in situation we will work with unknowns definitely. Alright, if we don't have unknowns in the denominator, it will be wonderful. It will be easier for us to manage the vectors, and that is the benefit of letting the ratio to be beta is to 1 minus beta. Alright, but of course there are certain questions that when you do this is more meaningful, whereas some other questions, if you just let it to be mu and lambda, that will do fine as well. Right, so this is a ratio theorem. Alright, now that we have already known the ratio theorem, let's get back to example 4. Now in example 4, we're supposed to find this ratio AF is to AC, which is equals to 1:3, and the last time we did it in that way, the particular way, we went to find out what is AF in terms of AC, right? Then with this relationship, therefore we have this line segment in terms of the ratio in length will give us 1/3, so we could have answered this question. So how do we demonstrate that the ratio theorem is actually much quicker? So the ratio theorem will actually allow us to find AF in terms of AC in this form very much quickly. So let's look at this triangle. So this is a triangle, and I want to find AF in terms of AC, right? So in the question we already know that the ratio between DF and FE is 2:1. Alright, so using the ratio theorem, we can always find this vector AF. So AF, alright, the total number of parts are 2 plus 1, so 3. So 2 times AE plus 1 times AD. Alright, and we know that AE is half P. so 2 times half P, and we know that AD is equals to Q, and that's why we can get 1/3 P plus Q directly. Alright, so this is much quicker to the earlier method where we need to go through all this process. Alright, so the ratio theorem has its advantages. So similarly for the next example also, so we can also use the ratio theorem to actually calculate all these two ratios. Alright, and initially we actually use this method, right, which is a bit long. Alright, so if you use the ratio theorem appropriately, you can actually find these two ratios quite easily. Alright, so I will leave it to you for you to actually apply the ratio theorem for this question. In this section, we are going to understand what it means by dividing internally versus dividing externally. So let's look at this setup. It says that C divides AB internally in the ratio 2:3. Alright, so on this diagram, I have the line segment AB, and it says C divides AB, alright, internally. So that means the point C must be between A and B. Alright, since the ratio that C divides AB is 2:3, so that means this is 2 parts, this is 3 parts. So in essence, we have the ratio AC is to CB as 2:3. Alright, so if we are interested to find what is the position vector of the point C, so let's say in this question we are given the vector OA as A and the vector OB as B, and we are interested to find out what is the resultant the vector OC here. Alright, so using ratio theorem, OC is actually 2 plus 3 is 5 parts, and then 2 times B plus 3 times A. Alright, so we will get the position vector of the point C in terms of A and B. Alright, so when it says that C divides AB externally, that means C is actually outside of the line segment AB. Alright, and the question actually says that C divides AB externally in the ratio 2:3. So that means AC is to CB is 2:3. Because of this ratio, we know that C actually happens to be on the left side here, because then we will have AC as 2 parts and CB as 3 parts. With this setup, if let's say we are interested to find what is the position vector of the point C, given that we know the point A has a position vector A and then the point B has position vector B, so with this setup we can write down the position vector of A using ratio theorem. Right, so the total number of parts will be 3, so you have 2B plus 1 OC. Alright, so how to proceed if you're getting OC? What you need to do is just make OC the subject. So you have this is A, so you have 3A minus 2B. Alright, in example 11, you are given the position vectors of the point A and B as the vector A, the vector B respectively, with respect to the origin O. You're supposed to find in terms of A and B the position vectors of the point P, which divides AB in the ratio 3:7, the point Q, which lies on AB produce. So later we're going to understand what it means by Q lying on AB produce, such that the ratio of the line segments 7/3. And then the last one is the point R, which lies on BA produce, alright, such that the ratio of the line segment is 3/7. Okay, so let's look at the very first one. P divides AB, so P divides AB in the ratio of 3:7. So this will be 3 parts and this will be 7 parts. So by ratio theorem, I think this is quite straightforward. The total number of parts is 10. Alright, and then if we were to draw the origin somewhere over here, right, so this is a vector A, this is the vector B, and you're supposed to find the vector OP, right? So using the ratio theorem, will be 7 times A plus 3 times B. Alright, so that's it in finding the position vector point P. Alright, so the ratio theorem is actually very simple to apply. Alright, now let's look at the second part. Now in the second part, it says that Q lies on AB produce. So what does this exactly mean? So if this is a point A, this is B, so AB produced, that means the line AB is produced away from B. Alright, so Q lies on AB produced, that means if we were to produce a line AB, it means we lengthen this particular line, so that means Q must be on this side. Alright, and we are given that the line segment AQ is to the line segment BQ is in the ratio of 7:3. So based on this, AQ has 7 parts and BQ is 3 parts. Alright, so what are we supposed to find from the diagram? Therefore we can see that B divides AQ in the ratio of 4:3. So this part is actually 4 parts. Alright, so if we are trying to find out what is a position vector of the point Q, alright, so if we want to draw the origin, we can actually draw it something like this perhaps. Okay, so this is O. In this question we know A, we know the position of vector of B also. What we are trying to find is this vector OQ. Alright, so using the ratio theorem, based on this setup, the total number of parts will be 7. Alright, so it is actually 3 times A. Alright, why 3 times A? Because the ratio over here is 3 times this vector, so 3A. Then the last one is of course 4 times OQ. Right, so 4 times OQ. Right, so using the ratio theorem, we see this relationship. So our objective is to find the position vector of Q, which is OQ. So what we need to do is just make OQ the subject. Alright, then we will get the position vector of the point Q. Okay, now in the last part, part C, it says that R which lies on BA produced. So now the direction has changed. Okay, so this is AB, right, as what we saw just now. But now R lies on BA produced. Alright, so BA produced, so that means R is on this side. The ratio that the question actually provided us is that AR divided by BR is actually 3:7. Alright, so that means the same thing again. The ratio over this part is actually 4. Alright, so if you are interested to find the position vector of R, so similarly what you can do is draw the reference origin over here. Alright, we know that this is the vector A, this is the vector B, and we are interested to find the vector OR. Alright, so from this setup, the vector A using ratio theorem is again divided by 7 parts, so 3B plus 4 OR. Alright, so objective is to find OR, so what we need to do is basically make OR the subject. Alright, then we will be able to get the position vector of the point R. In example 12, we are given that 2 points have position vector A and B respectively with respect to the origin O. And then we have the point P, which is the midpoint of AB, and the point Q, the midpoint of OP. Then the line AQ produced cuts the OB at R. Now in this question, actually the diagram is not given. Alright, so for such a question, you need to actually ensure that you draw the diagram. Alright, so first it says that we have 2 points with position vector A and B. So what we need to do is just mark a point A, point B, then the reference origin. So this is a vector A, this is a vector B. Alright, then they say P is a midpoint of AB. So you extend the line segment from A to B. So this is AB and P is the midpoint according to this statement. Alright, so we mark a point P and make sure that this therefore is equal to this. Alright, then next is they say Q is the midpoint of OP. Alright, so once we have already set up P to be the midpoint of AB, the point P is here. So this part here, it says Q is the midpoint of OP, so we need to draw the line OP and then find the midpoint Q. Alright, so this is the midpoint Q. Again, this length and this length is equal because Q is the midpoint of OP. Then it says the line AQ, so this is AQ. Alright, and then the line AQ is produced such that it cuts the line segment OB at this point R. Okay, so this statement basically it says that AQ produced, that means they all must lie on the same line. Alright, so when this is produced, it touches the line segment OB at the point R. Alright, so that's how we actually set up to draw this particular diagram. Without this diagram, it's going to be difficult for us to actually solve all these 4 parts. Okay, so what are the 4 parts? First, find the position vector of Q relative to O. Then find the vector AQ. Alright, and then prove that the position vector of the point R is 1/3 B, and then find this ratio. Alright, so the first one, in order for us to find the vector OQ, so where is OQ? OQ is here. So for us to find the vector OQ, basically we need to find what is the vector OP. Alright, the reason is if we were to look at this line, we know that Q is the midpoint of OP, right? If we can find the vector OP, that means OQ is just half of OP. Alright, so OP is actually quite easy. It's a ratio theorem. The ratio is 1:1. Alright, so it's a 1A plus 1B divided by 2. Alright, so in fact the OP, actually the formula for this part is the total ratio is 2, because this is 1:1. Alright, so 1 times A, you have A, plus 1 times B, you have B. Alright, so that's why you have half A plus half B. So therefore OQ is just half of this thing. Alright, so that is for part 1. Alright, so the position vector of Q is found already. Now I want to find AQ. So where is AQ? AQ is this. Alright, now AQ is quite easy to get, because I can look at this triangle. I can apply the triangle law of vector addition, alright, to be able to get AQ. Alright, so that will be here. Alright, so I want to find AQ, right? So based on the triangle law of vector addition, AQ is basically OQ minus OA, right? Because OA plus AQ will give me OQ. Alright, so that's why we have this relationship. Okay, so since we already know what is OQ, we will be able to get AQ. Alright, next, the second part is the objective is to find the proof that the position vector of R is actually 1/3 B, and then find the ratio of AQ is to QR. Let's use the fact that R is on both OB as well as AQ. Okay, alright, so since R is on OB, right, let's say OR is actually K times B. So that means we purposely put this ratio of this line is to this line as K is to 1:K. Alright, so OR is actually K times of the vector OB, and then because R is on AQ produce, alright, so we do the same thing. We let this be the ratio of lambda is to 1 minus lambda, so therefore AR is just lambda of AQ. Alright, so lambda. Okay, next we can see that OR equals to OA plus AR in this triangle. So this is OR. OR equals to OA plus AR using the triangle law. Right, so we know that OA is A and AR is given as this, we already found earlier. So we know that OR is equals to this. Alright, so there are two versions of OR. So OR is KB is equals to this. So what we can do is we can equate the two. Alright, and then we can make the comparison. Before we do that, this particular expression here need to be a bit more simplified. So we group all the A's together. Alright, and then the B on its own. So when we want to solve for the K, right, so what we need to do is compare the coefficient of B, which is K, together with the coefficient of B on this side, which is lambda over 4. Alright, then we will be able to get this relationship. Okay, so to get the other relationship, on this side actually we have 0 plus KB, but the 0 here actually is a 0 vector, because in fact we actually have 0 times A. So what we can do is we can compare the coefficient of A, which is 0 over this side, with the coefficient of A, which is 1 minus 3/4 lambda. So with that we will be able to get lambda 4/3 and K equals to 1/3. Once these values are found, easily we can actually get the position vector of r, because we know that OR is KB, so therefore we can prove it already. Alright, so together with the value of K and lambda, we can therefore find the ratio of AQ is to QR, because we can establish this. Alright, how come we can establish this? Because lambda is 4/3, right? We already put down here AR equals to lambda AQ, so this will be 4/3 AQ. Alright, so with this, then we can actually draw from the figure that is AQ is to QR is equals to 3:1. Now there are 4 applications of the dot product. Alright, so the first application is to show that two vectors are perpendicular. We have seen this before already. So if I were to give you two vectors A and B, how do you check that these two vectors are perpendicular given that they are not zero vectors? What you need to do is you just do a dot product. If you get the zero scalar, then it means that the two vectors are perpendicular. The other application is, of course, from the definition of the dot product itself. You can see that this is the angle between the two vectors. So in fact, you can use this definition to find the angle between two vectors. Okay, so whatever that is printed for you, cosine theta equals to A dot B divided by modulus of A modulus of B. So therefore theta is the inverse cosine of that term. This one shouldn't be memorized at all. What you need to do is just remember the definition of the dot product. Alright, because from the definition of dot product, you can always make cosine theta the subject and then do inverse cosine, you will actually get this formula. Okay, and bearing in mind that theta is between 0 degrees and 180 degrees inclusive. Alright, so if theta is acute, you will realize that A dot B is going to be a positive number, so bigger than 0. And if theta is obtuse, A dot B will be a negative value. Now let's look at some examples. In this example, you are asked to find the angle between the two vectors. The two vectors is given in the IJK form, but we would like to work in the column vector forms because it's easier to manipulate. Alright, so A is 2, negative 1, 2, and B is 3, 1, negative 5. Alright, so the dot product is actually quite simple. So you just take the two vectors and then do the dot product by multiplying the x component together, add to the multiplying of the y components together, and add to the multiplying of the z components together, we would get negative 5. Alright, and then we go and find the modulus of A, which is and the modulus of B, which is both 3 and root 35 respectively. So using the definition of the dot product, alright, we can make cosine theta the subject. Alright, and then we just need to input in all the things that we have found. A dot B happens to be negative 5, modulus of A is 3, modulus of B is root 35. Okay, now from this number itself, we have a sense that this is a negative value, right? So if this is negative, that means we would expect the theta to be obtuse, and indeed it is obtuse. Okay, I will leave the review question for you to review it yourself. Alright, another important use of the dot product is to find these two things, what we call the length of projection and the vector projection. Now let's do a little bit of unpacking from the terms used. The first one, length of projection. So when we see the word length, it suggests that this thing is a scalar. Alright, length refers to magnitude, so therefore length of a projection actually refers to a scalar. Alright, then the second one is vector projection. So vector projection, from the terms used, will suggest that this is a vector. Okay, what do we mean by length of projection? The length of projection of vector A onto the vector B, it is as if you take a torchlight and then you shine it on top here. When you shine it on top here, you will actually get a shadow, and the shadow actually falls like this from A to N. Alright, so this particular shadow here is a length from A to N. So the length of projection of the vector A onto the vector B is actually this particular length. Alright, so how do we obtain this particular length? from this point we go to a point N, where N must be the foot of the perpendicular from the point C to this line. Alright, so that is basically the length of projection. Now what is the vector projection? Vector projection of the vector A onto the vector B is actually referring to this part as well, but not the length or magnitude, but it refers to the vector. So the vector projection of the vector A onto the vector B is actually referring to this particular vector from here to N. Alright, so this vector AN. So actually it is referring to the vector AN. Alright, so the proper definition, the length of a projection of vector A onto the vector B is defined as the scalar product of the vector A with the unit vector of the vector B. And the reason we put a modulus is because we want to just have the positive absolute value, which will give us the measurement of the length. Right. So in this diagram, that particular length of projection of vector A onto vector B is actually this length here from A to N. Okay, so the formula is basically A dot B unit vector with the modulus. Now B is actually the unit vector in the same direction as the vector B itself. Alright, now how do we prove this formula? It is actually quite simple. You are actually quite familiar with this idea, because we are basically talking about the angle in a right angle triangle. Okay, so the proof goes like this. Now say theta is acute, this theta is acute. Now cosine of theta, alright, according to your identity for cosine, it is actually the adjacent side divided by the hypotenuse. So you have AN divided the modulus of A. Okay, so from here we can find the length of AN. Length of AN, right, is actually modulus of A cosine theta. Okay, so remember that this length of AN is actually the length of the projection of vector A onto vector B, this particular part here. Alright, so now from the formula itself, the modulus of A dot B unit vector, if we were to apply the definition of dot product, is basically modulus of A times the modulus of the B unit vector times the angle in between. Now because the B unit vector, right, is parallel to B, the angle between A and the B unit vector will also be theta, so it's cosine theta. Now what is the special thing about the unit vector? The magnitude is 1. So if the magnitude is 1, so that means we are left with modulus of A cosine theta. Now because in this particular proof I'm assuming that theta is acute, alright, so the modulus of this term inside here will remain to be the same, and we actually get the AN. Alright, the proof, in this proof I'm using theta to be acute so that it is easier for you to understand, but actually it also applies for when theta is obtuse. We will still get the same result because of the modulus. Okay, alright, so this is a third application of the dot product to find the length of projection of vector A onto the vector B. Now this formula need to be memorized, alright, because it is very useful. We're going to use it in vectors 2 as well in vectors 3. The fourth application of the dot product is to find the projection vector of A onto B. So what is the vector projection of A onto B? Alright, so just now the length of projection of vector A onto B, the length of projection of vector A onto B is actually this part here, the green line here. Okay, this part from A to N. Alright, so from A to N. And what is the formula? The formula is modulus of A dot B. Alright, so this particular length, alright, has this formula. But in this section, right, the fourth application, we're not interested in the length anymore, but we're interested in the actual vector, which is A to N. Alright, it's a vector. What is the magnitude of this vector? The magnitude of this vector A to N is actually this value. Alright, but what is the vector? Okay, so the vector actually has this formula. What you need to do is A dot B unit vector, and then you multiply to the unit vector again. This will actually give you this vector. Alright. For this formula, you need to memorize. The explanation for this is actually in the later part of this lecture, which I will let you read on your own. Alright, but we can always use this formula without proof. Alright, so the vector projection of A onto B is actually, when you take the vector A, you dot with the B unit vector, you will get a scalar here. Then you multiply this scalar by the same unit vector B. Alright, and you will get the vector AN. Right. So after finding the vector AN, right, some of us might also be interested to find this vector which is perpendicular to the vector B. Alright, so to find this particular vector, right, in this direction, we just need to apply the triangle law of vector addition. We will be able to get it. Okay, so in this particular fourth application, the two formulas that we need to actually remember is the vector projection of A onto B. It has this formula, and this formula is critical to see that A dot B unit vector, right, is a scalar. So basically in this formula you are saying that you are multiplying this scalar with the vector B unit vector. Alright, and then to get this vector, simply don't memorize this. What you need to do is just apply the triangle law of vector addition, then you will be able to get this. Okay, so in this particular page, the thing that you need to memorize is this part. Alright, the vector projection of A onto B. Okay, and of course the length of projection, this formula you still need to remember also. Okay, so you can see that there's a bit of similarity, right? Okay, the length is actually referring to this part here. Okay, so basically the vector AN, right, you're actually taking the magnitude of AN, you multiply this number, right, to the unit vector B. Okay, remember our concept earlier on of unit vector? I told you, right, if I have a unit vector U hat, right, so the definition is U the vector divided by modulus of U. So actually the vector itself, right, is equals to, you take the magnitude of U, you multiply by the unit vector of U itself. Right, so this formula, this definition of a unit vector, which gives you this definition for any vector, right, is similar to what you see here. Okay, so to find this vector, what you need to do is you need to know the magnitude, and then you need to know the direction that the vector AN is parallel and in the same direction with the vector that you're using. In this case, it's B unit vector. Alright, the projection formula is applicable whether AN is in the same direction as B or in the opposite direction of B. Alright, the same formula actually applies. Alright, so the reason behind why it applies is all stated here. I will leave it for you to actually delve deeper into it on your own. Alright, we will try an example first. Okay, now in example 19, you're given two vectors, alright, A and B. You're supposed to find the length of projection of A onto B. Alright, so we in vectors question, it's good to draw a diagram to have a visualization of what you're doing. Right, so in this question we're supposed to find the length of projection of vector A onto vector B. So the way I always draw my diagram is, if I want to find the projection of something onto something, right, this B here I always put it horizontally. Okay, then this one I purposely make it this way. But of course, some of you are saying, right, actually this vector A, right, why not is actually facing the other way? Alright, is it possible? Yeah, yes, it's possible, but just to simplify matters, we take it to be like that. Alright, so what is the length of projection of the vector A? Is basically this line here. Alright, you drop a perpendicular, then this is the line. Now in our formula just now, the vector A is actually stated like that, right? Okay, so if the vector A is stated here, if you drop the perpendicular, it is still the green line, so it doesn't matter. Alright, so it doesn't matter whether the initial point of this vector is on the vector B or not, we can still find the projection of A onto B, because you can see, right, no matter how I move, Alright, as long as you drop the perpendicular, the green line doesn't change at all. It is the same length. Alright, so in this example, I just draw the vector A as off away from the vector B. Alright, so using the same formula, alright, so A dot B, alright, I will get 14, and then the magnitude of B is root 14. Alright, so based on the formula where I want to find the length of projection, is basically A dot B unit vector, right? And this will actually give me A dot B. B unit vector is actually the vector B divided by B magnitude itself. So in fact, this formula can become A dot B divided by B modulus. Okay, so that's what you're going to see. Alright, so this is what I've written here. Alright, so A dot B divided by B modulus. A dot B we already found to be 14. Alright, divide by the modulus of B root 14. Because everything is positive, we can remove the modulus, and therefore the length here is root 14. So this green length here is actually has magnitude root 14. Okay. Now in example 20, you are given another two vectors representing the position vectors of 2 points A and B. You are asked to find two perpendicular components of A if A is resolved into one component which is parallel to B. So this is A, right? So one component which is parallel to B is this green part here, and then the other component which is perpendicular to B, which is this purple part. Right? So actually the formula has already been covered. Alright, so ON is basically the length of projection of A onto the vector B. So basically we use the same formula. Now to find this vector NA, basically we use the triangle law of vector addition. Alright, so I will let you evaluate this on your own. Alright, so because the formula is what we've just covered. Okay, so the only thing that you need to understand about this question is when they say two perpendicular components of A resolve into one component which is parallel to B, that means this is the one of them. Then one other component which is perpendicular to B is this one. Right? Alright, we still have this section onwards to go on to, but I'm going to pause here. So after listening to this lecture with this file, you will need to go to part 2, alright, for the rest of the lecture.